All right, welcome ladies and gentlemen. 6.2 dot products using some more stuff with vectors, or doing some more stuff with vectors today. We're going to look at the very basic idea of what's called a dot product and a somewhat complex thing called projection. Kind of a cool little thing, but it's always kind of complicated. All right, so let's get right into it here. First of all, let's look at what does a dot product mean. If I was to give you two vectors where u is the vector u1, u2, and v is the vector v1, v2, I have a property or a thing here. This dot in between the u and the v is not multiplication. It's a big, big dot that represents, or not a big, big dot, but it's like a bold dot between u and v that represents what's called the dot product. You know if that you did 3 and this little symbol between the two, that tells you to add the two numbers. If you were to say 3 dot 2, that tells you to multiply the two numbers. But the thing is, when I do u dot v, that means dot product. You notice how I said it, u dot v. It's not u times v. I can't say that enough. Well, u dot v is a very simple process saying, hey, let's take the x-coordinate of the first vector times the x-coordinate of the second vector, and I should not have put those little triangle brackets there. And let's add it to the y-coordinate times the y-coordinate, and you're going to get a number. So the dot product results in a constant. And what I want you to take a note of is on page 514, a couple of the products. And things along the lines of u dot v is the same thing as v dot u. You can kind of verify that pretty quick. One of the big ones, though, is a very kind of interesting one to me. Is u dot u is equal to this funny looking thing. And if you recall from the last section, that funny looking thing is the magnitude. So if I did the dot product of a vector on itself, I get its magnitude, which is kind of cool. So the dot product of itself is the magnitude. So you notice you don't even have to do the distance formula, I guess. Or sorry, not magnitude, magnitude squared. I wrote that wrong. But you get the square of the magnitude, which then you can square root to find the actual magnitude. All right, so that's what I was just saying. U dot u is the magnitude square of vector u. And let's just do a quick couple examples here. These are supposed to have triangle brackets on, not like before. Dot product is super, super simple. It's used in a couple little areas here coming up, though. All right, so 3 times 5 plus 4 times 2 is 15 plus 8, which is 23. See, nice and simple. Some of you guys are overcomplicating this next question, the i's and the j's. Don't bother about what I was saying with the 1, 0 and the negative 1, or the 0, 1. Just say that if I have 2i minus j, I just have the vector 2, negative 1. Dot product with the vector 3, negative 5. And you'll notice how easy this is. 2 times 3 is 6, plus negative 1 times negative 5 is 5, and I get 11. Super easy. Dot product is so easy. Let's see where we might be able to use dot product. The angle between two vectors, between u and v, is actually one area we're going to use this. Now, there's kind of a long proof of this particular formula, and it's basically just using the law of cosines. When we use the law of cosines, we get cosine theta is equal, I'm going to write this a little bit bigger here, and I'm going to have to erase it, but cosine of theta is u dot v over the magnitude of u times the magnitude of v. And then if I wanted to find theta, obviously we'd take the cosine inverse of this thing. Now what I want you to make a note of here, u dot v is a number, the magnitude of u is a number, and the magnitude of v is a number, which means this entire fraction is just a number. So I can take the cosine inverse of just a number. That's not a big deal. And again, I said something about the proof. There's a proof on page 516. You could kind of think about it. I'm sure most of you could probably kind of figure it out, or some of you at least. So let's say I have the vector 2, 3 and the vector negative 2, 5. And I want to find the angle between the two vectors. So cosine theta is u dot v. So I got to find u dot v. U dot v is 2 times negative 2 is negative 4, plus 3 times 5 is 15, is 11. And I also have to find magnitude u. So magnitude u, you can do it a couple different ways, but I just like the Pythagorean theorem version or distance version. Magnitude u is the square root of 2 squared plus 3 squared, so 4 and 9 make 13. And I need to find the magnitude of v, which is the square root of negative 2 squared is 4, and 5 squared is 25, so 29. And that means I can now plug these things in. So u dot v is going to be 11 over the square root of 13 and the square root of 29. Well, theta is going to be the cosine inverse of this kind of ugly fraction. And if you make sure that you plug this in correctly, you're going to get, let's see, cosine of 11 divided by square root 13, square root 29, 55.49 degrees. Remember, if you want fractions like this, if you hit alpha, and then, not the arrow, don't hit arrow, get rid of that. Alpha, and hit y1. Sorry, not y1, it's y equals, gosh darn it. If you hit alpha y equals, it will bring up a little thing, and you want in/d. It will make a fraction bar for you. Okay, some of you knew that already, some of you did not know that already. That's in case you want to make sure that you get things in the right spot for this fraction. That way you can actually see the denominator. All right, so angle between two vectors, not too challenging either. Very simple cosine problem using the dot product and using the magnitude of the two vectors. Now, you do get a new word today, other than just dot product. You get a new word called orthogonal. Orthogonal. Well, orthogonal basically means, okay, so two vectors are orthogonal if the angle between the two vectors is 90 degrees. Now, some of you are like, well, no, if things come together at 90 degrees, that means they meet at a right angle, or they're perpendicular. Right, but in geometry, two lines are perpendicular, or two rays are perpendicular. However, orthogonal, we're talking about vectors. So we had to kind of get a new name for this. Vectors are orthogonal when they meet at a 90-degree angle. Lines are perpendicular when they meet at a 90-degree angle. Slight difference, and I know some of you are like, well, who cares? You're right. It's a little bit like, why did they do that? I don't really know. So you could figure out if the angle between two vectors is 90, that means basically cosine of, let me reword this. We know that cosine of 90 degrees is 0, which means if I said the cosine of theta is equal to u dot v over magnitude u magnitude v, if the numerator is 0, that means cosine of theta equals 0, which gets me 90. So I'm looking for when two vectors have a dot product of 0. And you could do a pretty quick little question. And really the questions are they going to be orthogonal? So let's just think about u being the vector 2, 3, and v being the vector -6, 4. I just want to see if they're orthogonal. Well, that just means figuring out if the dot product is 0. So let's figure out what is u dot v. U dot v, 2 times -6 is -12. What happened here? 2 times 6 is -12. Sorry about that. Don't know what happened. And plus 3 times 4, which is 12. Well, that does equal 0, and therefore theta is 90 degrees. Very simple. That means they are orthogonal. The two vectors meet at a 90-degree angle. All right, so let's look at the hard problem. This is the hardest thing we're going to do today. It's the last thing we're going to do today, and it's called projection of vectors. What we are going to be doing is figuring out how much you have to hold on to if somebody's going down a hill. All right, so it's used to determine effective force in the direction of another vector. That's all well and good. You pull on a block of wood on a floor at a certain force and angle. What's the force actually being applied to the block? So say you have this block of wood, and you are pulling in this direction. And it's on a table. Now, if you pull at a certain force, then yeah, the block's going to come off, whatever. But really, if you pull in this direction, the block is going to be moving in this direction. And it's kind of like how you are as a kid. You pull things across a floor. You're pulling at a vector like this, but it moves in a vector like this. Now, this is not a complex formula, but here's the formula for how to find the projection. This is, I'm going to rewrite this in a little bit more fraction friendly here, u dot v over the magnitude of v squared times vector v. And this is projecting v onto u. And I'll explain really where we are going with this. Now remember here that u dot v is a number, magnitude squared is a number, therefore we can multiply by the vector. All right, so we have this guy sitting on a sled on the side of a hill that is at a 45-degree angle. So we have this hillside, 45-degree angle, and you got this guy sitting on a sled. He's ready to go down the hill. The combined weight of John and the sled is 140 pounds. So that means gravity is 140 pounds. It's pulling down, straight down. And you are, or John, I guess, or Roger, I guess, is up on the top of the hill, and he's trying to hold John from going down. And you need to know, can John hold on to him? How much do you actually need to be able to hold on to? Do you need to be able to hold 140 pounds? Probably not, unless John is John is on a cliff. He's off the side of a cliff. Then yeah, you need to be able to hold 140 pounds. But it's not 140 pounds here. So what we're going to do, we're going to draw the hill like I just did. We are going to say that F, or gravity, is going to be the vector 0, -140, if you'd rather this, because it's not going left or right, it's going straight down, so we think of this as a negative. Then we're going to say that the hillside is my V. So finding projection of V onto F, that sort of idea. The hillside sits at a 45-degree angle. And what's nice is the length of the hill doesn't matter. The length of the hill doesn't matter, so we're just going to say the magnitude of the hill is 1, which is cosine 45 sine 45. The magnitude of this vector is 1. And now we're going to use the formula. So the formula says to take f dot v. So f dot v. Cosine 45 is root 2 over 2. Times 0 is root 2 over, is 0. Sine 45 is root 2 over 2, and times negative 140. Sorry, I keep putting the vector symbol there. Cosine of 45 times 0 is 0. Plus, sine 45 is root 2 over 2 times negative 140 is going to be negative 70 root 2. Now, it's over magnitude squared. Well, if magnitude is just 1, it's going to be divided by 1. And then it's going to be multiplied by vector v. And vector v is really square root 2 over 2, square root 2 over 2. If I do this math a little bit here, 0 plus this, that's just negative 70 root 2. Well, I can multiply the root 2's in there, and I get negative 70 times the vector 1, comma 1. And then I want to find the magnitude of this vector. So this is really the vector negative 70, comma negative 70. And the magnitude of this vector ends up just being negative 70 times the magnitude of 1, 1, by the way. The magnitude of 1, 1 is root 2, so I get, really, in positive numbers here, 70 root 2, which is approximately 99 pounds. Which means all you need to be able to hold, even though John weighs 140 pounds, all you need to be able to hold on to is 99. That's kind of cool. And you'll notice this is the only place that we're going to use this particular formula because of the type of class that we're in. And this is basically the question that I'm going to be asking. Going down a hillside at a certain angle, can you hold the person up? Okay, I'm going to leave you guys with that. The bell kind of worked out for me. It hit right at the end. There you go. I'll see you guys tomorrow.